Welcome to the last part of this course, Calculus 1. So in this part we will discuss differential calculus. We will start with the notion of limit of a function. So today we will discuss the definition of limit of a function via the notion of sequences, and we will also see some examples. What is the limit of a function? The limit of a function is a fundamental concept in calculus concerning the behavior of the function near a particular point. The concept of limit appears in the definitions of continuity and differentiability. So you consider a function f from D to R. So what is D? D is the domain of this function, and this is just a subset of the set of real numbers. So this is a single real variable function and real valued function. And then you consider a point C. So it should satisfy certain condition that D contains an open interval around C except possibly the point C itself. So D should contain these. So that should be the condition. Okay, and then we can talk about the limit of this function f at the point C. Okay, so what should be the condition? That your domain D that should contain an open interval around this point C except possibly the point C itself. That the function f has a limit L, some real number, as x tends to this point C. If f of x gets closer and closer to this real value L as x moves closer and closer to C. That as x gets closer and closer to C, that this function value f of x should get closer and closer to this value L. And then we say that f has a limit L as x tends to C. So we will give precise definition of this notion, but at least we should analyze some examples to get some idea. Okay. So sometimes we write f of x has a limit at the point C. So let's analyze this function. So this function, this is a function from this set to the set of real numbers. Okay, so domain is R minus this singleton set 0. Okay, and then what should be the limit of this function at the point x equal to 0? Okay, so the concept is that as x gets closer and closer to 0, then this function value, whether it gets closer and closer to a particular value or not, that we need to check. So if we just see first few values, so if x is 1, then this function value is this one, and if x is 0.1, so 1 by 10, so then this function value it is this one, and if x is 1 by 100, then this function value it is this one. So we can see, so this data I have collected from Wikipedia, and we can see that as x gets closer and closer to 0, this function value it is getting closer and closer to the value 1. So in this case, this function f of x it is not defined at 0, but as x becomes closer and closer to 0, the value of this function becomes arbitrarily close to 1. So in this case, we say that this function f of x equal to sine of x by x, this has a limit. So here is another example. You just consider this function f of x, it is whose graph is given by this. Okay, so up to x naught it is given by this graph, and from x naught onwards this is given by this graph. So at x naught it is taking this value, and before x naught it is given by this graph. Okay, and let's analyze that whether limit exists or not. So the notion is that as we get closer and closer to this x naught, we have to see that whether this function value it is getting closer and closer to a particular value or not. That we need to check. In this case, let's consider this sequence. Okay, so if we approach from the right side and we get closer and closer to this value x naught, so let's consider this sequence whose nth term is x naught plus 1 by n. then as n tends to infinity, this sequence value it is tending to x naught. Yes, we can see that if we approach from the right side to x naught, then this function value it is given by this graph, okay, and it will be approaching to this value, okay. So this f of yn it tends to this value L suffix 2, so this is given by this. And if you consider this sequence, if n tends to infinity, then this sequence value it is tending to x naught. So here we are approaching to x naught from the left side. So if we approach to x naught from the left side, then we can see that since the function value is given by this thing, so in this case this f of z suffix n, so this value it is approaching to L1, okay. So we can see that if we consider two different sequences, so both are approaching to x naught, but their function value they are approaching to two different values. So in this case we say that limit of this function f of x does not exist at this point x naught, okay. So what about this point? If you take x1, so whether limit exists or not at this point for this function. So the function f of x has a limit at this point x1, okay. What about this function? So this function it is this is a function f from R to R. So here both domain and codomain are set of real numbers, and this is given by this, okay. So if x is greater than 0, then this function value is given by this graph, and if x is less than 0, then this is just fixed value y equal to 1, and at x equal to 0 it is given by this thing. Now let us see whether limit of this function exists or not at x equal to 0. So in this case f of 0, this function value it is 2, but this limit of f of x at x equal to 0, that will be 1. Why? Because if we approach to x equal to 0 from the right side or from the left side, we can see that this function value it will be approaching to this 1, okay. So the limit of f of x at x equal to 0 it is 1, though the function value f of 0 it is 2, okay. So and next we should give the precise definition in terms of the sequences of real numbers. So before that we should fix some notation, okay. So you consider delta some positive real number, then the delta neighborhood of a point C in R it is defined to be this open interval, okay. So if this is the real line, so suppose this is your real line and C is somewhere here, okay. So then this open interval I am talking about, so it is given by all these points lying in between C minus delta and C plus delta, okay. So it is just collection of all points x such that absolute value of x minus c is less than delta, or collection of all x such that c minus delta less than x less than c plus delta. So it is all points in this range, but we are excluding these points c minus delta and c plus delta, okay. And the deleted delta neighborhood of a point C it is defined to be, so we denote in this way n prime of c comma delta. So it is just this open interval minus this singleton set C. So we are excluding this point C from this open interval, okay. So it is just collection of all those real numbers such that 0 less than this absolute value x minus c less than delta, or in other words this is a collection of all real numbers which lie in between c minus delta and c plus delta, but x is not equal to c. So we are excluding this singleton point, this point C, okay. And here we give the definition of the limit of a function via the notion of sequences. So you consider this function f from D to R, where D is a subset of R, so we call it the domain of f, and we want to talk about the limit of this function f at the point C. So this point C, it should satisfy certain condition. What is that? So C be a point such that D contains a deleted R neighborhood n prime of C comma R of C for some positive real number R. So what I mean that D contains this deleted R neighborhood. So this open interval minus C. So here D may or may not contain the point C. So in this situation we can talk about the limit of this function f at the point C. And what is that? So we say that the function f has a limit L, some real number L at this point C. So we say that the function f has a limit L at C if it satisfies certain condition. What is that? So if for every sequence x suffix n in this set which converges to C, this function value f of xn, this sequence, it should converge to L, and this thing should holds true for every sequence which converges to C. Okay, not just a single sequence which converges to C. Okay, so if for every sequence which converges to C and this sequence term it lies in this set, that means that no term of this sequence it is same as C, and all the terms here it is lying in this set D. Okay, so if a function it satisfies this condition at this point, then we call that f has a limit L at C. What is that condition? That for every sequence x suffix n in this set, if it converges to C, then this sequence it should converge to L. And in this case we sometimes we write that f of x tends to L as x tends to C, or sometimes we write limit x tends to C, f of x it is same as L. Okay, so let's analyze this function and let's see whether this limit at this point exists or not. So already we have given this argument, but so since this is the precise definition, let's try to verify whether it is satisfying this condition or not. Okay, we have two sequences, both converge to the same point x0, but their function value, so f of yn it converges to L2 and f of zn it converges to L1, and these are not equal. So it is not satisfying this condition, and therefore f of x does not have a limit at this point x0. But f of x it has a limit at this point. So if you consider x1, it is so one can see from the picture that whatever sequence you consider, if it approaches to x1, then this also approaching to this value. Okay, and so and one can prove it theoretically also just by considering the equation of this graph. Okay, and now we should analyze some more examples. So this example we have already considered. Okay, and let's verify whether a limit exists or not at x equal to 0. Okay, so this function value f of 0 is just 2, and this limit x tends to 0 f of x, so I claim that it is 1. Okay, so let's verify that using this definition. Okay, so here you consider a sequence in this set d minus 0, and this sequence it converges to 0. So this is an arbitrary sequence in this set which converges to 0. So we need to prove that this sequence f of xn it converges to 1. Okay, so this is given, limit n tends to infinity, xn is 0, and we need to show that limit n tends to infinity, f of xn it is 1. Okay, so how to prove? So we want to show that this 1 it satisfies epsilon n condition for this sequence. So you consider epsilon greater than 0, some positive real number, and for this epsilon we want to find a natural number n such that beyond that natural number the distance between this nth term and 1 it is less than epsilon. Okay, so before that, so let's first analyze this absolute value, the distance between this term and 1. Okay, so f of x, this absolute value f of xn minus 1, so it is, if this nth term, if it is less than 0, if it is negative, then f of xn, it is just 1. So in this case it is 1 minus 1, so it is 0. But if this nth term, it is greater than 0, so since this nth term, it belongs to this set, so xn is not equal to 0. Okay, so either xn it is negative or xn is positive. Okay, so if it is negative, then this distance it is just 0, and if it is positive, then f of xn it is just xn plus 1, and in that case this distance it is just this x suffix n. Okay, so from this observation, now we will use this fact. Okay, so since I should write that since limit xn n tends to infinity, it is 0, so there exists n such that this xn minus 0 it is less than epsilon for all n greater than n. And from here I can see that this distance f of xn minus 1, that is also less than epsilon for all n greater than n. So ultimately we are getting that for this epsilon there exists some natural number n such that this distance it is less than epsilon beyond that natural number n. Okay, so this one it is satisfying the epsilon n condition for this sequence. Thus we can conclude that limit x tends to 0 f of x, it is just 1. Okay, and here is another example. So in this case you set your domain D is r minus 0, and you consider this function f from D to r. So it is defined by this thing. So f of x is same as minus 1 if x is negative, and f of x it is 1 if x is positive. And then what can you say about the limit of this function at x equal to 0? So whether it exists or not. Okay, so I claim that f of x does not have a limit at x equal to 0. Okay, so let's try to verify this condition. Okay, so here we have to disprove that we have to find two sequences xn and yn both converge to 0, but this function value, so their limits are different. Then we are done. Then we can conclude that this f of x it does not have a limit at x equal to 0, because if f of x has a limit at x equal to 0, then whatever sequence we consider, if that sequence converges to 0, then this function value it should converge to a single value. Okay, so but here we are getting two sequences both converge to 0, but this function value, so f of xn it converges to 1 and f of yn it converges to minus 1. Okay, so from here we can conclude that this limit it does not exist. Okay, so if you consider this sequence xn is 1 by n, so since it lies in this positive side, so its function value it is given by 1. So this sequence it is just constant sequence and it converges to 1. And if you consider this y suffix n, so it is minus 1 by n, so this also converges to 0, but so this all the terms lying in this range on the negative side of x axis. So this function value f of yn it is given by this minus 1. Okay, and so again it is a constant sequence and it converges to minus 1. Okay, so from here you can conclude that this limit of f of x at x equal to 0 it does not exist. Okay, and what about limit of this function at other points? Okay, so for the above function limit x tends to c of f of x, it exists for any c not equal to 0. So you can, so let's consider some point here. Okay, so this is your C, so this is some real number not equal to 0, and then you have to verify that it satisfies that condition. Okay, so whatever sequence you consider if it approaches to C, okay, then you can prove that your function value it approaches to this fixed value 1. Okay, so if I should write if Zn tends to C, okay, then f of Zn it tends to 1. Okay, so for any sequence Zn. Okay, so thus limit x tends to C, f of x it exists when C is not equal to 0. And that's all.